and thanks for watching Edupedia World videos. We saw in the previous video an introduction to the Schrodinger equation, and in this video we look at a time-independent version in which generally it's easier to solve problems. So I'll write the Schrodinger equation once, minus h squared by 2m del square psi by del x squared plus v psi. So both of these are the partial derivatives. Psi, if we are talking about one dimension, will be a function of x and t, and if we are talking about three dimensions, may be a function of x, y, z and t. For this video and for a few later videos, we'll only talk about one dimension. Also, the potential difference if we're talking about one dimension will depend on x. If we are talking about three dimensions, will depend on x, y and z. And generally the potential can depend on time as well, but we will assume right now that it is independent of time. Now what does that exactly mean, it is independent of time? It means that it is not explicitly dependent on time. The potential energy of the particle, the formula for the potential energy, is not directly dependent on time. That does not mean that the potential energy is constant. It will change as the particle moves. Just as an example, if we were to keep a particle in gravitational potential, then the potential energy would be minus mgh. Now as the particle moves, the height h will change, which means the potential energy will change. So the potential energy is dependent on time, but only through h. So this is intrinsically independent. What would be a potential dependent on time? Say the potential energy was minus mgh for the first 10 seconds, then minus 2 mgh after that. In that case, the formula for potential energy itself is dependent on time. It is changing with time. And we will assume that that is not true. Let's say a particle is attached to a spring. In that case, the potential energy is always half kx squared. Now, of course, as the position changes, x will change and the potential energy will change. But the formula does not depend on time. The formula is half kx squared. So this is again a case of potential energy independent of time. If instead we said that for a certain time it's half kx square, then for the remaining time it's kx square, then the potential would be dependent on time directly. But you can see, as from examples you've done in previous classes, that generally the potential energy is not dependent on time. Potential energy formula will either be minus mgh, half kx square, or whatever value it is. So in our course, in our scope of discussion, we will assume that the potential energy is directly independent of time, though that does mean that as x, y and z change, the potential energy changes. That is obviously true. Now, one of the interesting things about quantum mechanics is that this equation, the Schrodinger equation, is incredibly complicated in trying to find solutions. If you have a very simple potential energy, V of x, y, z, if it is very simple forms, some forms which we'll discuss in a few videos, then you can solve the equation completely. But for complicated formulas of potential energy, it is often impossible to find the exact solutions, and we have to use approximation methods, which we'll study in advanced quantum mechanics, which is not in this course. However, for a few basic simple systems where V of x, y, z, or V of x if we are just talking about one dimension, for a few systems where this is simple enough, we can actually calculate the complete solution, and then for advanced problems, we actually try to modify these simple cases to try to match the advanced cases. So first we'll study a few simple cases such as the harmonic oscillator, the free particle, and the infinite square well. Then later, as we move on to complicated potentials, not in this course, in a later course, we'll see the simple problems can be modified a little bit to solve the complicated problems. So for these simple problems, the first step to solve the Schrodinger equation is something which is used quite often in physics, especially when you have an equation involving partial derivatives. Remember, by the way, I shouldn't have written y and z because this equation assumes that it is dependent on x. If it is dependent on y and z also, then this would have been del square psi by del x squared plus del squared psi by del y squared plus del squared psi by del z squared. Right, so right now we're talking about one dimension and psi is dependent on x and t. Now, del psi by del t is the partial derivative with respect to time, meaning x is assumed constant. Del 2 psi by del x square is the double derivative, but only partial with respect to x, keeping the time constant. And partial derivatives are themselves quite complicated mathematically. So the first step to solve any equation like this is a process which is called separation of variables. So we will not solve the exact question first. We will solve a simpler version of this question where we will assume that psi of x comma t can be actually separated into the two variables, meaning it is not a function of the form of 3xt plus 2x squared t cube. It is a function which is a product of two functions, one only of x and the other only of t. So we are assuming that psi is something like 3x squared plus 2x multiplied by 3t plus t cube. So this form is totally dependent on x and t because both of them are in every term. But here we have a separation of variables. Psi of x of t, if it is of this form, then it can be separated into two functions, one only dependent on x and the other only dependent on t. So that is what we'll assume. Now every solution will not be of the form of separation of variables, but it is a subset of the solutions that we'll find out, and later we'll see that modifying these solutions we can actually calculate every solution of this equation, of course for a few simple cases. So right now we'll assume that psi of x of t is a product of two functions, psi of x multiplied by phi of t. Now this is the capital psi, this is the small psi, so I apologize if they don't look different enough, but everything we've done till now is the capital psi, and capital psi is dependent on both position and time. But we think of it as a separation of variables. We think of it as a product of two functions. One, psi of x, this is small psi, which is only dependent on x, and the other, phi of t, which is only dependent on t. So let's try to input this into the Schrodinger equation and see what we get. Again, what are the assumptions? I'll repeat them. The first assumption is that the potential energy intrinsically is independent of time, which is true for almost every case you've seen up till now in previous classes. Potential energy expression does not directly depend on time. Also, we are assuming that this function we are trying to find out, psi of x comma t, is actually a product of two functions, one only of x and the other only of t. So let's input this into this equation. The first thing we'll get is del of psi by del t. Now, this is the partial derivative of this function with respect to time. But in that case, we can assume that this function is constant because partial derivative means assuming that x is constant. So this will come out to be psi of x multiplied by d phi by dt, phi of t. Now notice here we had a partial derivative because this was a function of both x and t. But here you do not have a partial derivative, you have the direct derivative because this is only a function of time. Similarly, del of psi by del x will be the partial derivative, and that will be the derivative of psi of x assuming the other term is constant. So that will be d psi by dx multiplied by phi. And from that we can get the double derivative delta psi by del x squared, which is what we need here, and that will be equal to d2 psi by dx squared into phi. Always notice the difference between partial derivative and direct derivative. Partial derivative means that the function is a variable of more than one variable. A direct derivative means this is only a function of x and this is a function of t. So let's input these into this equation. So the first term we get is iota h del psi by del t, which is psi into d phi by dt. This is equal to minus h square by 2m del squared psi by del x squared, which is d2 psi by dx squared into phi, and then plus v times psi. Now what is psi? Small psi multiplied by phi. So small psi multiplied by phi. Right. Now what we'll do is we'll divide this whole equation by psi and phi. So what we'll get is, I won't write it again. So this is v, we divide both sides by psi and phi, and here dividing it by psi and phi, you get 1 by phi and you get 1 by psi. Now here we'll use a concept which is used many times in advanced physics, and it is a very important concept, so I advise you to listen closely. The left side, phi, is a function of t. So the LHS of this equation is only a function of t. And the RHS, similarly, the RHS does not have phi, it only has psi. And it has v, which we've assumed to be x. This is where we use the fact that v is independent of time. Because v is independent of time, only dependent on x, the RHS is only a function of x. But these two are equal. So we have two things which are equal. One only depends on t and the other only depends on x. So imagine that x is the same but t changes. Then the LHS would change but the RHS would remain the same. But that cannot be true because the LHS is equal to the RHS. So in such a situation, when you have an LHS only dependent on one variable equal to an RHS only dependent on the other variable, there is only one possible conclusion, which is that both are constant. Because otherwise you could keep one variable constant and change the other variable and the LHS would stay the same and the RHS would change, or vice versa. So that means the LHS is equal to the RHS and both are equal to some constant. For reasons which will appear in a moment, both the constants, we'll call them equal to E. So this is our ultimate equation. Iota h 1 by phi d phi by dt is equal to minus h square by 2m d2 psi by dx square into 1 by psi plus v, and both sides are equal to E. Now notice that we've gotten a time-independent equation here. The right side equal to E is a completely time-independent equation, and this part, this is equal to E, is what is called the time-independent Schrodinger equation, because we do not have any term involving time here. We only derive a time-independent Schrodinger equation when this is true, when the potential is independent of time. In that case, this is called the time-independent Schrodinger equation. And now we can actually go further and we can actually solve these two sides as well. The LHS is equal to a constant E and the RHS is also equal to the constant E. In that case, you can change x or t, but no side would change because they are both equal to a constant value. Now let's try to solve these. First, we'll try to solve LHS equal to E, and then we'll solve RHS equal to E, which is the time-independent Schrodinger equation. So the time-dependent version of it would be iota h into 1 by phi d phi by dt is equal to E. And this is quite easy to solve. From this, what we get is dt goes towards the right, and so what we get is 1 by phi d phi will be ln phi. So when you integrate it, this side and this side, so iota h ln phi is equal to et. From that, what I get is phi is equal to some constant, let's say phi naught, into e to the power et by iota h. Now another thing we'll do here is this phi naught, we'll just take it to be 1. And the reason for that is the net function which we are interested in, capital Psi, is equal to psi multiplied by phi. So whatever the constant is for phi, we can just take that into psi as well. Right? So the whole constant will come into psi, and phi we can just take it to be this. And a better way to write this is phi of t is equal to e to the power minus iota et by h. So we've solved half of the equation. We knew that psi was psi of x multiplied by phi of t, and this is both of x and t. And phi of t we found. Next step is to find psi of x. And for that we have the equation minus h square by 2m 1 by psi d2 psi by dx squared plus v is equal to e. This is what is called the time-independent Schrodinger equation, which is derived from the basic Schrodinger equation because there is no time term here. Now this, we cannot go any further with this until we know what v of x is. Remember, up till now we have only used one property of v of x, that is, it was dependent only on x, not on explicitly on time. So after this, we can only go further once we know exactly what v of x is, and in the next few videos, we'll see specific simple cases for v of x and try to solve psi of x for those cases. right? But right now, what I would like to do is focus on what exactly psi of x of t tells us. So it is of the form, the net equation psi, capital Psi of x comma t is basically psi of x multiplied by e to the power minus iota e t by h. So this is what we've got. And only after knowing what b of x is, we can go any further. But let's study what this is for a moment, because this has so many special properties. These sorts of functions are called stationary states. And the reason they are called stationary states is because when a particle is in this state and you measure a quantity, let's say position, momentum, kinetic energy, you always get the same value regardless of time. So let's see why that is. Yeah, so let's say you try to measure the probability density. We know what the probability density is. It is mod psi squared. We saw this in the previous video, which is equal to psi star times psi. And these are all capital Psi's. Now what is this equal to? When we input this value, it is equal to psi of x times e to the power minus iota et by h into the complex conjugate, which is psi star of x into e to the power the complex conjugate of this, which is iota et by h. Now we see that these two terms cancel and we simply get psi of x multiplied by psi star of x. Now this is small psi, which is equal to mod psi squared. So we see that the probability density, which we saw in the previous video, was the probability of finding the particle at a point or between 2 points. The probability density is completely independent of time. So any solution of the Schrodinger equation which is of this form, in which you have separation of variables, one a function only of x and the other a function only of t, which we've solved to be e to the power minus iota et by h. Anytime you have a wave in this form, a wave function or a state in this form, then the probability density will not depend on time. That is the reason they are called stationary states. In fact, it's not just the probability density, the expectation value of every variable will be independent of time. So we saw the expectation value of any function f of x, which was a function of position and momentum. So I should actually write x comma p. But remember, the position operator was x and the momentum operator was h by iota d by dx. So if you have something like kinetic energy, which is p squared by 2m, or anything else which is created by x and p, then the expectation value was given by integral of total psi star multiplied by f multiplied by psi dx. Now you can see f of x comma p does not depend on time. So again we'll have the same thing. This will be integral of psi star times e to the power iota et by h multiplied by f of x comma p, where p could be an operator like this, but it also only depends on x. Psi of x multiplied by e to the power minus iota et by h dx, and once again these two terms cancel. So the expectation value of anything is also constant. So when a particle is in a stationary state, which means it is in the separation of variables form, then you always find a certain value for the average of position, a certain value for the expectation value of momentum, kinetic energy, potential energy, angular momentum if you're dealing in 3 dimensions, and so on. Everything has a fixed expectation value which does not depend on time. Now again, I would like to mention one thing. The expectation value is constant does not mean the actual value is constant. The actual value would be a sample of data and you would get many different values based on the probability. But the average value of all those samples will be independent of time in a stationary state. Another important property of stationary states is that they are states of definite energy. And here we'll see why we actually use the constant capital E for the LHS and RHS during the separation of variables. And we'll see another more simplistic and more satisfying form of the time-independent Schrodinger equation. What is the time-independent Schrodinger equation? Minus h square by 2m 1 by psi d2 psi by dx squared plus v is equal to E. Now we'll take psi on the right side, and so we get v psi equal to E psi. Now what does this look like? If you notice closely, P was h by iota d by dx, the momentum. So what is the kinetic energy operator? That is P squared by 2m. That is h squared by iota squared, which is minus 1, d squared by dx squared. And this is the kinetic energy operator referred to as T, P squared by 2m. So we see that minus h squared by 2m derivative, double derivative with respect to x squared is basically the kinetic energy operator. Now when an operator is of the form of a derivative, then you apply it on psi, it actually differentiates that psi. Similarly, V is the potential energy operator. But V does not have a derivative, it is simply a function of x. So when you apply it on an operator, you just multiply it. So what we have is T psi, the kinetic energy, plus V psi, the potential energy. This is often referred to as H psi, where H is written as the Hamiltonian. It is just T plus V, and it is the total energy operator. And this, we are told from this RHS, is equal to E psi. Now remember, these are operators, which means they don't necessarily multiply. When you have V of x, it multiplies. When you have a kinetic energy, it differentiates. And this is another more satisfying way to write the time-independent Schrodinger equation, which is simply that H psi is equal to E psi. Which means when you apply the Hamiltonian operator or the total energy operator on psi, you get E multiplied by psi. So that tells us that E is the total energy. So in stationary states, not only is the expectation value of everything constant, but E is the total energy, and it is the energy of this state. Now in E, we don't have to talk about expectation value, and the reason for that is, let's try to solve the expectation value, the variance of psi. So when we do, let's say, the average or the expectation value of H, we know what that will be, psi star. And now I'll only write small psi because the e to the power iota t by h gets cancelled, multiplied by h, the operator psi dx. Now h psi, we already know from the time-independent Schrodinger equation, is equal to E psi, where now you only have a multiplication with psi. So E comes outside, we have E integral of psi star psi dx. But we already know that from the normalization of the wave function, this is 1. So it is equal to E. So the expectation value of H is equal to E. But not only is that true, what is the expectation value of H square? This is something which is not also true, momentum or position, only true for energy. The expectation value of H square, again psi star times H into H. And when you have a on an operator, it's just applied twice. Psi dx. Now H psi gives me E psi. Once again, H multiplied by E psi gives me another, so it gives me E squared times integral psi star psi dx, which again is equal to 1. So this is E squared. So what is sigma H squared? The variance. That will be equal to H squared minus H whole squared, which is equal to E squared minus E squared is equal to 0. But what does it mean to say the variance is 0? It means every sample gives you the same value. So while for potential energy or for just kinetic energy or for position or for momentum, we get a range of values based on the statistical interpretation or the probability density, and the average value of those is fixed with time. For the case of total energy, not only is the average value fixed with time, but every measurement gives you the same value E. And that's why these functions which we wrote as psi of x comma t, capital psi, is equal to psi of x e to the power minus iota e t by h. These are referred to not only as stationary states, but as stationary states of constant energy E. Now this is the difference between energy for a stationary state and something else like position. The position's value will give you a range of values, but the expectation value or the average of those range of values will be independent of time. For a measurement of energy, you will not get a range of values. Every time you measure the energy of a particle in this state, you will get the value E every single time. So it is a state of constant energy. Now finally, you might have wondered, what is it about this restriction that gives us a lot of solutions or is even useful? We started by assuming that psi of x comma t is a product of two variables, psi of x and phi of t, where phi of t turns out to be this thing. But what if there is a solution to the Schrodinger equation which is not of this form? Then you're missing solutions by assuming this. Well, that is taken care of by a theorem in mathematics. We'll not go into the details of the theorem. It is beyond the scope of this course. But what it basically says is that every solution rather, to the Schrodinger equation can be expressed. Now we're talking about even solutions which do not have separation of variables, as a linear combination of stationary states. Which means, let's say you have one capital psi of x, we'll say psi 1 of x, which turns out to be psi 1 of x e to the power minus iota e1 t by h. So this is a stationary state of energy e1. Let's say you have another function, psi 2 of x is equal to psi 2 of x e to the power minus iota e2 t by h. Right. So in that case, you can have a third solution to the Schrodinger equation, and the third solution will be a linear combination of these, which would be, let's say, C1 psi 1 of x e to the power minus iota e1 t by h plus C2. C1 and C2 are simply constants. They can be complex as well. Psi 2 of x e to the power minus iota e2 t by h. So this is a capital psi of x, which is a linear combination. And in fact, the mathematical theorem states that every solution, no matter how complicated or simple it is, can be expressed as a linear combination. So let's say you have 30 solutions like this. You are able to find 30 different or 10 or 5 different solutions of the form of psi 1 is equal to psi 1 e to the power minus iota e1 t. And you have a number of these solutions with different energies e1, e2 and e3. Then every single solution can be written as psi of x comma t is equal to summation I is equal to 1 to n, whatever the total number of energies is, Cn psi nx e to the power minus iota en t by h. And the theorem says that no matter how complicated the solution is, you will always be able to find certain values for Cn. We'll see how to find those values in a later video. But for every solution, you can find appropriate values of Cn such that a linear combination of the stationary states gives you that solution. Now remember, a linear combination of stationary states is not a stationary state. If a particle is in this state and you measure the energy, it will always be E1. If a particle is in this state and you measure the energy, it will always be E2. But if a particle is in this state, a linear combination of two energies E1 and E2, then if you measure the energy, you might get E1 or you might get E2. So now you do not have a stationary state. This is not a stationary state. In fact, even if you just measure the probability density, psi sti, you'll see that all the complex conjugates won't cancel, and even the probability density would be dependent on C1, C2, and time. So a general solution can be written like this, which can have any number of terms for different energies. It may even have infinite terms for infinite different energies. If you find a solution of the time-independent Schrodinger equation, which has an infinite different discrete values of energies, as we will soon enough in harmonic oscillator. But so you find the stationary states assuming the separation of variables, and then every solution can be expressed as a linear combination of stationary states for appropriate constants Cn. By the way, these energies E1, E2, which we get as solutions to the time-independent Schrodinger equation, are called allowed. So not every energy will be allowed, only values which you get from the Schrodinger equation, and we'll see how we get allowed energies later on, will be allowed. So a lot has happened in this video, so let me give you one small recap of it. We started with the normal Schrodinger equation, not the time-independent version 1, iota h del psi of x comma t by del t is equal to minus h square by 2m del squared psi by del x squared plus v of x times psi. This is the assumption that v only depends on x. Also, the assumption is that we are looking for separation of variables psi of x comma t such that this is equal to psi of x multiplied by phi of t. When we input this here and we solve it, we get two values, one LHS, one RHS. Both of them, the LHS is only dependent on t and the RHS is only dependent on x, and because they are equal independent of t and x, they both have to be equal to a constant, and we name that to be equal to e. From that we are able to find phi of t, which comes out to be e to the power minus iota e t by h, and psi of x we have to find out depending on the potential. So then we get the net psi of x comma t is equal to psi of x multiplied by e to the power minus iota e t by h. Now this is a subset of all of the solutions of this equation, because this is the solution set of equations in which we have assumed separation of variables, and these we found out have some properties which give them the name stationary states. The properties of these stationary states, which are gotten by assuming separation of variables, are that the probability density is independent of time, the expectation value of every single operator, potential energy, kinetic energy, position, momentum, is independent of time, and also the energy is constant, not the average of energy. The energy is constant, which means if you measure the energy of this solution, of this wave, you will always get it to be equal to E. Finally, the net complicated solution, which is not separation of variables, is given by summation I is equal to 1 to n Cn, a linear combination of all of these states, psi n of x e to the power minus iota en t by h. And this is how you have been able to solve the Schrodinger equation, time-independent Schrodinger equation. The only thing that is left is to find psi n of x or psi of x, and for that we need to know what v of x is, and in the next few videos we'll see some special simple cases of v of x, such as the infinite square well, the harmonic oscillator, the delta function potential, and so on. And from that we'll be able to see how to totally find the total solutions. Thank you.